Good morning. Let's get right into it. Day 13, part 2. You know, when I first saw this problem, I did think, well, it's got to be the kind of like the two equations, two unknowns. But the problem, the thing that I just went, we'll just brute force it, knowing that the part 2 would be a little more difficult in some way. This is easy to do because you're told you only have to do 100 iterations. So that's brute forcing it is not a big deal. Obviously, with part 2, you can't. And I started thinking maybe this is like a linear optimization problem. But I also thought, well, that's also very complicated or somewhat complicated. But I was interested to just go down the route of, is that possibly the way to go? And just reading up on it and learning about something that I had vaguely heard about in the past, but never actually done anything with. So, but long story short is, yeah, I think the two equation, two unknown part is the way to go. So let me get some music going. I also do have a time limit this morning because I'm going to go see Nosferatu this morning. So looking forward to seeing that. Where are my notes? So basically you have these two equations where, of course, the A's button on the machine and its x increment is AX, then there's AY, and there's BX, BY, and then this is the prize or the results X, result Y. And so basically these two have to be satisfied. Okay. And I went through the math and generalize them so that A is this and B is this. So for each machine, we just plug in the one for A and we plug in the one for Y. Of course, there may or may not be a solution. So the thing I got to check is when I do this for A, well, one, it has to be positive, and two, it has to be, because you can't have negative clicks of a button, and it also has to be an integer. So if this division has to have no remainder. And the same thing for B then. But that should allow us to do the calculation quickly. The first thing I'm going to do is back this up and do this for part 1 first. So we're going to take out our initial implementation and let's get some music going. If anything, it's background for me. So, all right. So what we want to do is we want to say for each machine, not that, this. Let's take this. Of course, none of that makes any sense. There. Okay. Oh, wait a minute. No, this I did the wrong and fastest syllable thing. This. There. Now we say if there. So div rem should give the quotient and the remainder. If a quotient is greater than 0 and a remainder is equal to 0, then we can move on. Okay, so now we know that we have at least A works out, and in all likelihood B will work out as well. Just be explicit. I always like being explicit with that. So that's the numerator. And then we want to say var b quosh. The denominator is just machine y, right? X. If, good guess. So now we have valid values for the A and the B. And so what we can do is we can say total tokens plus equals 3 times A quotient plus B quotient. And then we return the total tokens. Now again, this is part 1. We're not adding the 10 trillion number yet to it, but we'll get there. So let's make sure my math is all correct here. So ry, b increment, minus by, rx, ay, bx, by, ax, rx, ax, and then we just divide by bx. Okay. So let's run this against our test. And it passes. Okay. Let's do day 13. See if we get the same answer. And we do. Okay. So now we do also have a test case for part 2. Or yeah, for part 2. So now this is exactly the same, except what are we gonna do? We gotta add this to the prize. space it out a bit so that I can actually understand. Excuse me. So now, anywhere stupid, I'm almost certain I need to go to a doctor for this stupid thing that I just cannot get rid of. All right, so price offset. This basically is anywhere we see the rewards in place. We could do it on the machines and add them here, but it's 6 cents, 1/2 does any other. Okay, so I think I got them all. Reward, offset. Reward, offset. Reward, offset. Okay, so now if we do the same thing for part 2, we should get a different answer. What is it? Oh, it doesn't tell us. Yeah, okay, fine. We don't know. Part 2. Damn. Well, it was good while it lasted. Well, dang it. We could make these all big integers. I don't know if I'm actually running into a overflow. Because what is the... I mean, it's 5 orders of magnitude larger. So we shouldn't have that problem. I hate this when I think, oh yeah, the part 1 works and it works the same way and part 2 works, yay, and then you do this and it all falls apart. We are getting some answers. I mean, I guess it doesn't hurt to... By the way, there is an int 128, in case you're curious. I highly doubt that this is the problem, but actually we should change this to a there. Yeah, it still gives the same answer. So even with a arbitrarily long the problem with this is that there are no other solutions. This either is or isn't it, you know? So it's not like I could have possibly found more than one. This might be a very short stream because if I can't figure this out, I'm just going to be staring at a screen for hours on end. Oh. Okay, so that works. Huh. That's interesting. It's interesting because it gives an answer that's extremely huge here. Oh my God. You know, it would help. It would help if you put in the right input. How did day 12 input not even cause it to... Like, I'm shocked that didn't just blow up completely. What? How does this work for part 1 but not part 2? Both of them are getting the same input. Where does it actually break? Why are you running 12? What is going on here? Oh. Oh, Jesus. Yay. Happy Sundays. Well, at least it was just stupidity on my part of not putting in the right input file, so that's good. All right, we've got part 2 done. We can move on. Yay! Okay, let's check out our happy calendar. Bet this looks a lot happier than what Nosferatu is going to look like later. Day 14, restroom redoubt. One of the historians needs to use the bathroom. Fortunately, you know there's a bathroom near an unvisited location on their list. And so you're all quickly teleported directly to the lobby of Easter Bunny headquarters. Unfortunately, EBHQ seems to have improved bathroom security again after your last visit. The area outside the bathroom is swarming with robots. To get the historians safely to the bathroom, you'll need a way to predict where the robots will be in the future. Fortunately, they all seem to be moving on the tile floor in predictable straight lines. You make a list, your puzzle input, of all the robots' current positions and velocities, 1 robot per line. For example, each robot's position is given as P equals XY, where X represents the number of tiles the robot is from the left wall, and Y represents the number of tiles from the top wall when viewed from above. Right, that way. Top left corner. Yep. Each robot's velocity is given as a XY again. X and Y are given in tiles per second. Positive X means the robot is moving to the right, and positive Y means the robot is moving down. So velocity of V means that each second the robot is moving 1 tile to the right and 2 tiles up. The robots outside the actual bathroom are in a space which is 101 tiles wide and 103 tiles tall when viewed from above. However, in this example, robots in a space which is only 11 tiles wide and 7 tiles tall. Yeah. The robots are good at navigating over and under each other due to a combination of springs, extendable legs, and quadcopters. Of course, so they can share the same tile and don't interact with each other. Visually, the number of robots in each tile in this example looks like this. Why though? Zero. I don't get it. This one has a 2. All right, so Oh, I'm reading the song. Here's the 3-0. Here's the 3-0. That's where you get the 2 there. Okay, never mind. I was reversing. Yeah. These robots have a unique feature for maximum bathroom security. They can teleport. When a robot would run into an edge of the space they're in, Instead, teleport to the other side, effectively wrapping around the edges. Here is what robot P2 for V2 minus 3 does for the first few seconds. Yeah, so it just keeps going like this. Asteroids. I was watching a playthrough of somebody doing Galaga and getting like, I think it was like 5 million something. And it was just some random video I saw on YouTube this morning, and it's one of those nostalgia things. Galaga is one of my favorite games of all time, and of course it would wrap from the bottom and then come back up in the top. Asteroids they would just keep wrapping around. So this is the same thing. And if you don't know what asteroids and Galaga are, you're too young. The historian can't wait much longer, so you don't have to simulate the robots for very long. Where will the robots be after 100 seconds? In the above example, the number of robots on each tile has elapsed to look like this. To determine the safest area, count the number of robots in each quadrant. Oh, so you take out the middle line there, and of course I can't do that this way. The quadrants contain 1, 3, 1, 2, 3, 4, and 1. Multiplying these together give a total safety factor of 12. Predict the motion of the robots in your lists within a space which is 101 tiles wide and 103 tiles tall. Odd, yay. What will the safety factor be after exactly 100 seconds have elapsed? Well, you have a robot, and a robot has a characteristic of a position and a velocity and iteration, right? Because we're going to iterate over the robots over time. Or you could just say a robot has a position and velocity, and then the iterations will just be what the new one is. And so we figure out what the new position is based on its velocity. And of course we mod it so that we make sure that we're modding so that it goes across whatever way it's going, so that we get that going. And then we just have to figure out the quadrants. So the one quadrant would be like X going from 0 to whatever the halfway point is, -1 over there, and then you find robots that are within, X being that and that, and Y being that and that. What happens after a trillion, quadrillion iterations? You want to bet that's what part 2 is? And so what you have to do is you have to find patterns in your velocities and stuff like that. I bet that's what part 2 is. All right, so let's do our... So we're going to need a parser to get all the robots. And what we want is we shouldn't have to worry about big integers. Public sealed record position, which has an int of X and an int of Y. Public sealed record velocity. Let's do these just to be a little, because they're not coordinates per se. And then a public sealed record robot has a position, and a velocity. There. Okay. This is obviously wrong. But at least it gets the thing to shut up. So now we save our robots is equal to a new list of robots. And we return. Come on. Can I not code? Apparently not. So let's go look at our input again. So we want to split on a space. And then we want to get a split on the substring. Parts of 0, substring. So we get the substring of that. And then we split again on a comma. And what are you saying here? Range operator, yay! Whee! What now? Wait, what did you just do? That was odd. Huh. Okay, whatever. So now we have our position parts. And we can get our velocity parts. Which is basically the same thing as this, except the 1. Yeah. And so now we get of our robot is equal to a new robot, where we say a new position. We want to say in parse, position parts of 0, culture info. Let's really separate this out. That'll make it easier to... Okay, so we get the position, and we want to get our new velocity. Which is basically the same as this, except it's velocity parts. There. So that gets us all the robots. Oh, and then we got to add it. Thank you. Okay, so we get our robots, and then the first part we want to do for var Eyes, what is the... $100. So we want to get each robot for thank you. I wish when it gives a suggestion it would format it correctly too, but oh well, can't ask for everything. So now what we want to do the input in terms of your you don't know what it is from the input. I'm surprised they didn't code that in and say the first line is going to be those, and then everything after that would be that. That you actually have to input it outside of the input file. Oh well. Seems like an odd one. And so robot with its position. This might be a little bit too wonky with a deconstructor or a wither, sort of. So var new position is going to be a new position where it's going to be the robot's current position X plus the robot's velocity of X change mod X max. Come on, figure it out, figure it out, figure it out, figure it out. Stupid computer. And the Y is going to be the Y change mod Y max. So we can say robots at R is equal to what the robot is with position equal to new position. Oh. Well, la-dee-da. Fine. All right, so that should give us where all the robots are. And now we need to get quadrant counts. First quadrant. Ooh. Ooh. Sorry, I got a little excited. I think we can do this in one shot. We could say no. We could get a count of all the robots where where the position is greater than or equal to 0 and the R position X is less than what happens if you do a yeah, it rounds down. I keep forgetting that. So you're in there. You're in there. And then, and our position Y is greater than or equal to 0, and our position Y is less than or equal to. Because it's going to round down. And so we want to make sure that you're doing the 3. If you had a 7, you want to be 0, 1, 2, or 3. So that's the first quadrant plus 2, 3, 4. Now we want to be greater than seven divided by 2 will give us 3 plus 1 is 4. Well, we got to go, so it's got to be plus 2 of that. And then less than x max. And then the y is the same because we're just over in that quadrant. The third quadrant, x is the same, but y now needs to be this funky little value. And then y less than y max. And then this one needs to be this funkiness. And this funkiness. That's completely obvious, isn't it? Let's break it out even a little bit more. No. Oh my God, don't do that. It's horrible for it to do that. No, stop it, stop it, stop it. Actually, I'm going to format it a little bit more. We're going to put this up here. Yeah, it's a little bit more readable. At least to me it is. And quite frankly, that's what matters. Well, for this, because it's just my own code. That's it. Oh, no, it's not. I forgot. There's one more part. No, it could be. Except we have to multiply these together. I could see where this may go a little out of the bounds of numbers, so to speak. Let's see how far it goes with what we have. Let's get our input. This is the input. Except we also need $11 is at and you're saying this should be equal to 12. Of course, we don't have a part 2 yet. Zero, yay! Yeah, so whatever we did, we somehow got, once you get a quadrant where there is no robot, you automatically get a 0. So let's go off debugging. We should be able to see, do we get the right input? The positions were also given here, so we can look to see did we get them in the right position, and then we can see, is this fancy thing I'm doing utterly wrong and incorrect? Okay. So we get robots, we get 12. This is a little hard to read, but the last one is 9.5 minus 3.3. Okay, that looks right. Now what happens after the whole evolution? Well, we get a robot at... That should never happen. Okay, that's the problem. I have negative coordinates. And which I get why. I forgot about this. The mod doesn't remove the sign. So let's say you have or you could think of it that way too. Like if the velocity is a minus, it's actually the plus of the max. If that makes sense. So if your velocity is minus 3 in the y direction, and our y direction is 7, it's actually 4. because both of those give you the same it gives you the same result, if that makes sense. So either that, or I gotta say, what happens if you have let's say we had a 1 minus a 3 mod a 7. We get a minus 2, which is not what we want. What we can do is say always add and then you get the 5. So what happens if we had like a plus velocity? We get a 4. If we take off this factor, it's irrelevant. You had to do that. So that's a 6 cents, 1/2 dozen of the other. So we always take this and then we do the same thing here. That makes for, or we could do it when we're getting the still fails. Still gets 0. Well, we no longer have any positions that are negative, so that's good. So we get 3 there. Which is wrong. The logic says there should be only 1 there. So that's wrong. Yep, and we got 1 that's at 0. Yep. Yep. Well, something must be going kerfloofy with our logic here. We could do one with just this and see, are we getting the right behavior? And I think that's the same. I don't know if that's going to be right or not. Doesn't matter. Why are we still returning a big integer? But I don't care. Let's see what this does. So we should have one robot. It's in position 2, 4. Okay. And so what do we expect? We expect it's going to be in a new position of 4. Of 4, 1, right? Yes. Four, 1. Okay. So that was correct. And you can see that here. Now we do that. Of course, we're not going to do 100, but we don't care about that. Now the new position, we're at 4, 1. So we should be at 6. Well, y is 1. Minus 2 plus 7, 5. Yes, 5. Six, 5. That works. Okay, now we have six. So we should be going 8, but then we're going to rotate to 2, right? 5 minus 3 is 2. 8, 2. Okay, that makes sense. Get our robot. We should be at 10, 6 after this. 1. 10, 6. Okay, so that works. And now the last one should be 10 to 12. We should go to 1, right? As we do, and this should be 1, 2, 0, 1, 3. Okay, but it did that weird thing where it skips. It seems like we're getting the right positions. This is what we should see with our grid after we're done. Okay, so I'm kind of convinced that works. You know, I wish there was a really nice way to just... I don't want to ask Copilot. I really don't want to ask Copilot. Well, we could do it the hard way, I guess. So, do we have a robot at position X3, Y5? We do. Okay, so that's correct. Do we have a robot at position 5-4? Did I do that right? 0, 1, 2, 3. We do. Okay. And I want to make sure that I put robots that are in the same position and kind of put them in the same place. Do we have a robot at 9-0? 9-0. 9-0, we do. I know this is tedium. It is what it is. 4-5, I'm almost sure we do because we do. We want 4. One 6. We do. One 3. We do. We're almost there, folks. If I would 6-0. We do. If this was like 100, this would be really painful, but with only like 10 or 11, it's not that bad. 2-3. We do. Zero 2. We do. 6-0. Yeah, that's one of the ones that had 2. Right? Yep. Two more. 4-5. We should have had one of those already. I believe we did. Yep, we did. Okay. And let's get 11. Six, 6. And we do. Okay, so stop this for a second because I got the feeling the missing logic is missing in my missing brain here. I already see it. Do you see? Helps to have that in the right place. Still fails. So that wasn't it either. That was a bug. That wasn't the only thing, obviously. Well, we know we have, like if I sort this, there. Just to make absolutely sure we've got everything in the right positions. In case the guy looked down. Okay, so I am now convinced that the logic, damn it, the logic that I'm doing to get the robots in their final positions is correct. This is somehow messed up. I'm not doing this right. It'll be one of those things that should be that. We're saying there's 3 there. And that's incorrect. I should be seeing just 1. So something is wrong with this. Even with this first one. This first one... Oh, wait a minute. Am I... Yeah, X goes over there. And Y goes... This first one that I just copied, I'm trying to say is X 0 to this, and then Y down here. So it should be this region right here. And somehow that's coming up with 3. How could that come up with 3? X max is 11. 5. Right. Oh. It should be strictly less than that. There we go. We gotta rethink those. Okay, so this has to be strictly less. This has to be strictly less. This, if we did the 11 divided by 2, which gives us 5. We just want to make sure it's greater than 5, right? 0, 1, 2, 3, 4. 5 is forbidden, but 6 is okay. So just greater than that. I guess maybe I was overthinking it. Now what do we get? A pass. Let's give it a whirl. Learn my lesson. Okay, so 101, 103. Maybe give it the right file. Yay. Okay. All right. So git commit. Part 2. During the bathroom break, someone notices that these robots seem awfully similar to the ones built and used at the North Pole. If they're the same type of robots, they should have a hard-coded Easter egg. Very rarely, most of the robots should arrange themselves into a picture of a Christmas tree. What is the fewest number of seconds that must elapse for the robots to display the Easter egg? How? Oh, brother. One moment, please. Needed to reload on the coffee for this one. Well, I guess if I would have been paying attention to wrong tab. Well, that looks like a Christmas tree. It's an Easter egg, so somehow I got to remember what. No. 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 I do remember one of these having something with a robot. I just can't remember. Into a picture of a Christmas tree. Yeah, but what is the picture? I don't know. I guess I could just have it visually display what it looks like. After each iteration, I just clear the screen and I just print. And see if I ever get something that looks like a Christmas tree. And then I just print the iteration. I don't know. I'm fine. Let's just have some fun. So we're going to clear it. We're going to get the new positions. And then we got to print each line. Right? Thank you. That's exactly what I wanted. No, X max. You had it. Can you do just a bunch of characters? Come on. So we're going to do this for each Y as we go down. And of course, I'm going to have to make my terminal bigger to see this. And then I just do each one and I just keep hitting enter until I see. Oh, what I want to do here though is there, because we want line, not right. Because this is the first increment and then the second increment. And then I just have to control X to, or Alt F or whatever, just to stop the thing. Well, ain't that cute? Let's just see what this does. Now I'm reading this as most of the robots should arrange themselves, not all. I don't know if this is the right way to do this or not. Oh, that is obviously not the right thing. No, I want to make a character. I want them all to be the same character. I forget how to do that. Yeah, I get I know how to do that. What I mean is, could you do new string? Yeah, this. and the length of X. Ugly, but why is it not clearing out after every... Clears the console buffer and corresponding console window of display information. That seems like what I wanted to do. Yeah, console cleared. That seems really weird to do it that way. Because, I mean, just doing it this way is not clearing it. Like, that gives us increment 1. Ooh, that started looking like a tree. The problem is, if it's not right away, I got it. I'll take a screenshot of this char thing and I'll send it to a web search and say, does this look like a Christmas tree? That'll solve all my problems. At least I got this to work. It's ugly as hell, but it works. It's like the Matrix. Blonde, blonde, brunette. Ooh, that looks like information. If I wanted to be really fancy schmancy, I could do each color and then change the foreground color to either being like black for space, or white for the dot, and then it would be even more obvious. But just going to play with this for a couple minutes, and then obviously if this, see, it sometimes does this and then it does that. What does a Christmas tree even look like? Even if this isn't the way to do it, and you do know what, you find out what the structure is of the tree. This is like the game of life, in a way, sort of. See, there's like every so often it gets some in the bottom here and then it gets some there. And I wonder if that means it's like there, like it's converging to something. Well, I ain't seen a Christmas tree. This is like when Homer Simpson says, "Hey, let's play Hungry Hungry Hippos." And then you're like, "Oh, is that it?" I couldn't tell. Something looked like a shape. I'm kind of curious because wow, that was like blinding. Yay, they're all green. We'll do that for the and now we'll say for each of our display char and display, if display char equals that, rewrite the char. Now we know that's the case. Otherwise, else. And then we need to do a right line. That's a little slower. So you get this little clumping there. Not pretty, but I mean it's a little easier on the eyes, you know. I just don't like it that he did the right line. It wasn't putting the spaces. It should have. Why didn't it do that? Well, yeah, now it does that. That's great, but I want it to be spaces. There, that's fine. It's kind of fun. Except if it did make a tree, it would have gone by so fast I would not have seen it. And again, it doesn't have to be all of them, but just enough of them in a certain shape to say, yes, this is a tree. But where is it? Where is the tree? Is that a tree? Watch as the developer goes bonkers. It's almost like constellations. Ooh. You know, I'm kind of curious, did those happen in cycles? Like those clumps? You get a clump there, then you got a clump there, and then you get some time. I mean, this is just playtime at this point. And then you get a clump there. And you should get a clump in the middle. Yep, as you do. Okay, let's start over. I'm kind of wondering, are those happening at certain repeating... So that's 14. We'll call those the vertical clumps. Horizontal. So that's 14. Let's see if we can get some kind of pattern. I have no idea if that's what I'm looking for, but if the rest of it is just noise. There, 94. $115. $197. $216. $300. $317. Seems like the vertical clumps happen every 101 and the horizontal clumps happen every 103. Gee! That could be completely 101, 103. It's kind of funny though, yeah. But it like the starting value is 14, and then if it's 14 plus, like if the value mod 101 is 14, then show it. If it's 103, show it. Let's just try that. So we only display if increment mod x max is equal to, and the x max is 101, is equal to 14, or increment mod y max is equal to 94. Then we show stuff. And we wait for the user to give us some input. Let's try that. 114, 94, 115, 197. This could have nothing to do with the tree, but it's just interesting you get these clumps at these points, you know. I don't know. That looks like a Christmas tree to me. I don't know about you, but I got the feeling I'm going to have to look up somewhere what exactly is it looking for in terms of a tree. Because if I knew the shape, then you could say at every iteration, if you just look at all the robots, there aren't that much. And then, like, say it's the root of it, and then move down. And see, do you have other robots nearby that have that shape? Because otherwise, this is just... I just saw it. I just saw it. So it's around, once you get up to 6,000, slow down. Four, 5, okay, 6. What is that? That is 6377. It's a beautiful day in the neighborhood. That was pure guess. That was pure guess. Just, well, let's try just visually displaying it. And it was very clear. There's your tree. All right. Progress made. It's always good when you make progress, isn't it? Okay. That was kind of a garbage implementation, but hey, whatever works, right? And this one, there's no real way to time it as far as I could tell. Like, how would you know that you ran into something that looked like a tree unless you knew exactly what the shape should be? You just have to print this out. This is the only one that I could see that you can't really... I don't know. Anyway. All right. So let's look at our admin calendar. It's getting bigger. 28 stars. How much time do I have left? I've been going for almost 2 hours. Let's spend a bit of time on 15 and see where that goes. Warehouse woes. You appear back inside your own mini submarine. Each historian drives their mini submarine in a different direction. Maybe the chief has his own submarine down here somewhere as well. You look up to see a vast school of lanternfish. By the way, that was interesting. that it was a multiple sort of 101, 103, and it was those 14 and 90. That was a pure guess. If I didn't land on those, I would have had to do something like go through literally 6,000 pictures plus to find it. Of course, once you see it, even if it just flashes by, you could do like what I did is go, wait a minute, it was around this value. And so you could zoom right to that. But still. Anyway, swimming past you. On closer inspection, they seem quite anxious, so you drive your mini submarine over to see if you can help. Because lanternfish populations grow rapidly, they need a lot of food, and that food needs to be stored somewhere. That's why these lanternfish have built elaborate warehouse complexes operated by robots, of course. These lanternfish seem so anxious because they have lost control of the robot that operates one of their most important warehouses. It is currently running amok, pushing around boxes in the warehouse with no regard for lanternfish logistics or lanternfish inventory management strategies. Right now, none of the lanternfish are brave enough to swim up to an unpredictable robot so they could shut it off. However, if you can anticipate the robot's movements, maybe they could find a safe option. The lanternfish already have a map of the warehouse and a list of movements the robot will attempt to make your puzzle input. The problem is that the movements will sometimes fail as boxes are shifted around, making the actual movements of the robot difficult to predict. For example, as the robot, attempts to move, if there are any boxes in the way, the robot will also attempt to push those boxes. However, if this action would cause the robot or a box to move into a wall, nothing moves. Nothing moves, including the robot. The initial position of these are shown on the map at the top of the document the lanternfish gives you. The rest of the document describes the moves that the robot will attempt to make in order. The moves form a single giant sequence. They are broken into multiple lines just to make copy pasting easier. New lines within the move sequence should be ignored. Okay. Here's a small example to get started. Were the robot to attempt the given sequence of moves, it would push around the boxes as follows. So that's the initial state. Can't do anything. It goes up. Can't do anything, moves to the right. And it does. So you can push X number of boxes over so long as there is space between that and the wall. And walls can be within the warehouse. So you can't just say like it's the edge. You gotta include those as well. So we push, can't push, we push down, we can't push anymore. Go to the left, go down, go to the right, go to the right, go down, go to the left, can't go. Okay, so that's what you end up with, apparently. The lanternfish use their own custom goods positioning system, GPS, to track the locations of the boxes. The GPS coordinate of a box is equal to 100 times its distance from the top edge of the map plus its distance from the left edge of the map. This process does not stop at wall tiles, measure all the way to the edges of the map. So the box below has a distance of 1 from the top edge, right? Because it's a Y of 1, and this is 4. Because 1, 2, 3, it's position B4. Oh, so it's this 100 times and then plus 4. And you'll never have a 0. The lanternfish would like to know the sum of all the box's GPS coordinates after the robot finishes moving. In the large example, the sum of all boxes GPS coordinates is 1,000. Small example, it's that. So we have 2 examples. Okay. Predict the motion of the robot and boxes in the warehouse. After the robot is finished moving, what is the sum of all the box's GPS coordinates? And let's get our puzzle input right away. Is it gonna make a Christmas tree? So I think we're gonna need we need to know if on the map something at a particular coordinate is a wall, is a robot, which I guess we're the robot, we're moving it around. Maybe. And boxes. So we parse the input until we see an empty line. And then everything after that okay, these are different lines. That's fine. I just want to understand what the parsing is. As soon as we see an empty line, or we could parse until we see an empty line, or it doesn't start with whatever. And then now we know we're into positioning. And so that can just be reading the content as we go through it. That's not too bad. This gets those coordinates. So what we could do is say, we don't need to store all of the empty ones. So what we can do is like here at the initial state, we have to move there. So what you have to do is you have to look to see what's to the direction that you're going in. If it's nothing, you can't find an item. An item can be a wall, it can be, or a box. Okay. If you find nothing, you simply move your robot over that whatever direction you're going. If it's a wall, you do nothing. Those are the two simplest ones. If it's a box, you have more work to do. And now you have to see how many boxes are linked up. And if it's a box, now you have to look at that next position and say, is that a wall? Then we don't do anything. Because you can go as many boxes over you want, but if you end up hitting a wall at some point, it's the same thing. You don't do anything. If you find another box, that's your end, and now you have to search from there. If you find you don't find anything at that next spot, then what you do is for all of those boxes you found, you move them over that direction that you're going, and you also move your robot that direction. Sounds simple. Sounds simple. I don't know how much farther I'm going to be able to go on this. I already got 3 things done. So I'm going to time box this a little bit and not go too far on it. But okay. $15. Oh, that was interesting. That shows where that stupid string comparison. It must have thought I wanted to do a field or something. I don't know. We want to say we want to get 2 things. We want to get the map which is going to be a list of items. And an item has a symbol, either a wall. It's either the wall, the box, or the robot, and then its position. And then we also want to just get the list of movements. Okay. So we want to have an item, char type, and then where it's at. So the robot, this is going to parse input. This is going to give us a list of items. And the number of things doesn't change. Only the X's and the Y's are going to change. And a wall never changes. A wall stays where it is. And so this could also be a immutable array of string. So we could say here, var items is equal to a new list of items. And here we could say var items movements is equal to solution day 15 parse. Let's just keep it big integer. Actually, what we could do is use the mighty int 128, but nah, we won't do that. Just shut it up. If the data length is greater than 0 or equal to 0, now we know, Jesus, we can return items, and then we can return input at I plus 1. I just want to take like a subcontent of the string. I want to take a range of the string. Of the input. I mean, sorry. That ain't right. So give me everything after that index plus 1. Sure. If not, we've got some parsing to do. For content, sure. Our type is equal to the data C. If we don't get anything, we can just say return items and an empty thing. If that, or what is that? That's an O, right? That's not a 0. And then the at is the robot. If it's any of these, items.add, new item of that type. The X is what we're moving across with the C, and the I is that. I could actually make this a little bit more explicit. There, that's a little better. So now we're going to know where all of our items are. For each var so now we got to move the robot. So that will get us all the up, down, left, or right. If whoops, that's an up. Else if the movement command is to the right. Else if the movement command is down, which should be a V. It's a lowercase v, right? Yes. Else. There. Okay, so we'll do all the movements. Of course, it's going to be some logic. But we assume we do that. We assume we just do all the logic that I figured out. And actually, we want to find and there should be only one of these. If that fails, that means we didn't parse right. Okay. So we get the robot. Which is critical. Now here, what's the algorithm to do? So now what we want to do is go through all of the items that are boxes. So we get all the boxes, and the GPS sum is going to be whatever so it's going to be box.x plus 100 times box times y. No, that's not a box. That is not a box. There's a kid's book that does that. That's not a box. I remember reading it to my kids when they were younger. Can't remember. Is it a mouse in a box or something? I don't know. Okay, so we find the boxes. We add up all their things, which is basically the x plus the y. Okay. And then we return GPS sum. We're going to get the wrong answer. We know that. Well, let's just get the tests in for now. Okay. So we have a smaller example. Here's a smaller example. Part 1 small. And we don't have any of that garbage there. So the small should be 2028. And then the larger one was this one. What I'm more wanting to confirm is that this doesn't fail-ish, and we just see what we get. We're not going to get the right answer. There's no way we're going to get the right answer. But we do get something, which means it parses, I think, and it goes through and does all the work. We're going to verify that. By the way, it could get the right answer if for some magic the end result gives you the same GPS sum as the input, which is highly unlikely. But, you know. Wait, that should be a different... Yeah. Still won't work, but that's okay. That was close. I mean, it sort of should be bounded because even if you don't move them around, you're going to still get coordinates of where they are. So... Okay, so now let's just go through what this does. And we want to make sure that we're actually getting the right input, that we get the right robot, and that we're doing this right. Okay. Let's do it the large. Okay, so movements is length 10, and it should start with the and it does. 1, 2, 3, 4, 5, 6, 7. Hey, I can use ranges in C# correctly. All right. Let's look at our items. Okay, let's look at our robot. Robot is an at 4, 4. So this should be 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Got that right. Damn it. Okay. So it looks like we parsed our items correctly. I mean, I didn't check every one of these. But we did get boxes. Like there should be one at 3-1. Wait, one. Wait, whoa. That's wrong. It's saying there's a box at 3-1. Oh, I'm looking at the end. Look at the beginning. 1, 2, 3, 1. Okay. Funny that the robot ends where it starts, right? Oh, I was looking. Okay, fine. Okay, so yeah. Right. Blah-de-blah-de-blah. Blah, blah, blah. So it looks like we're parsing correctly. We're getting all of the items correctly. Let's just make sure that we get down to the right one. We should see that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We should see a bunch of items at 9 that are all walls. Yep, and we do. Cool. So it looks like we parsed this correctly. We parsed this correctly. And now it's just a matter of doing the logic that I mentioned before. Okay. Which, easy, right? Easy. But I'm going to stop here because I want to do a couple things before I go off and see Nosferatu. One of the things I'm going to do is check to see if Splinter Cell. I have downloaded all the Splinter Cell games. In fact, I need to make sure I've actually downloaded them. I think I have. Maybe I haven't. But maybe I can get that set up while I go off to watch Nosferatu. Or at least the first one. And then see if it runs. Because it's such an old game. You know, I've noticed that some games have some tweaks that you have to do to get it to run. So it'll be interesting to see if that even runs or not. But if it does, I may do a Splinter Cell stream starting, that series of 4 or 5 games that I got, and starting to get back into doing some gaming streams. I still have the goal of streaming all of Random.Code for 2024. I have almost convinced myself that I am not going to do any more Random.Code streaming. I may do the rest of the years just kind of like off to the side as fun little problems to work on here, there, and everywhere. But I don't know if I'm ever going to stream this again because it's a lot. But I enjoy it. It's just, it's a lot to get through while you're coding. But in any event, I have a good idea as to where to go with this. So one thing I want to say too is I don't need a hint on this. I don't mind people giving hints. I don't mind people giving suggestions, but I need to explicitly state I need help. I'm asking explicitly for help. If I'm not, then, please don't give it, because I really want to be on the struggle bus for as long as I can be until my patience is completely worn out and I'm like, I just don't get it and I need help. So, this one, I know where I'm going. I've run out of time and I'm going to pick it up later. So I'm okay with the progress. But yeah, I'm going to start doing some gaming streaming. My older son's like, what are you doing? You're doing boring coding again? I'm like, well, you don't watch my streams anyway, but if it's Splinter Cell, he might. I don't know. But, and I do want to get back into doing some gaming. I've missed it. So with that, I'm going to stop for now. If you've been watching now or you watch this pre-recorded later on, thank you for watching. I greatly appreciate it. Please subscribe. I was watching a streamer yesterday saying, let's get to that magic 1,000,000 mark. I'm like, yeah, I'd like to just get to 1,000 right now. But I would appreciate it if you subscribed. That would greatly help get me to that first 1,000 subscriber mark goal. So please subscribe. And with that, I'm going to stop the stream. Thank you all for watching. Take care, and I hope to see you in the future.